All right. Today we're going to start chapter number 7. And chapter number 7 basically is about the Earth. The planets formed from the solar nebula 4.6 billion years ago. This is what we did in chapter number 6. And now you're ready to visit the planets and get to know them as individuals. That will help you confirm your understanding of the origin of the planets and will reveal new principles of planetary evolution. We began our study with the Earth, and that means you must see your home world in a new way, not as a location for exciting vacations, international trade, and strategic political agreements, but as a planet. In this chapter, you will answer 4 essential questions. How does Earth fit among the terrestrial planets? How was Earth changed since it formed? What is the inside of the Earth like? How was Earth's atmosphere formed and evolved? Thinking about the Earth interior will help you answer an important question about science. How can scientists know about things that they cannot see? So this is basically what we're going to do. We'll try to survey our planets. The first part will be a travel guide, and then early history of the Earth, the solid Earth, the atmosphere of the Earth. So now let's go with the first part. In chapter number 6, in our solar system, we talked about 2 types of planets. We talked about terrestrial planets and Jovian planets, and we said the 4 inner planets basically are terrestrial planet, namely Mercury, Venus, Earth, and then Mars. So if we look at all these terrestrial planets, of course, we include the moon as well with the Earth here. So they have similar internal structures. That means they have liquid heavy metal core, liquid mantle or light rocks, and then we have solid crust. That's what we have it. When it comes to Earth, Venus, and Mars have atmospheres, and they are dominated by physical processes that we call greenhouse effect. Of course, Mercury is very close to the sun. It doesn't have an atmosphere. Venus, it has a very thin atmosphere, and it's believed that the solar winds basically has eroded all of this atmosphere. Earth is basically has an atmosphere that with the greenhouse effect gives us the comfortable temperatures that we have. Venus is very fiery, very hot because it has an atmosphere made of sulfuric acid and it traps in the heat, and that's why it's very hot. So how does the Earth fit among the terrestrial planets? Well, we're going to use Earth as a standard of comparative planetology. That means we're going to look at it when we look at the other planets. The terrestrial planets include the Earth, the Moon, Mercury, Venus, and Mars. We include the Moon when it comes to the Earth as well. Earth's moon included because it's a complex world and making a striking comparison with Earth. That's why we're going to it's be included. The terrestrial world differ mainly in size, but they all have low density crust, mantles of dense rocks and metallic cores. So they have the same internal structure. And then we're basically going to look at the craters on the surfaces, and we can see this very clear on the moon. So we look at what happens in surface erosion on the Earth. So what is the early history of the Earth? In chapter number 6, we talked about how the solar system evolved out of planetary nebula. And it was basically with a young star in the middle of a thin disk of dust. And then small rocks basically start forming and hitting one another and colliding. Finally, planets were formed, and Earth basically was formed along. So when it comes to the Earth, we basically have four distinct stages. The first stage, which we call differentiation. So when the Earth basically was forming from these two very small rocks, and they were hitting one another and so on. So it was very hot. And at that stage, basically, the Earth started differentiating, which means the denser material goes to the center, and of course, the less one will basically go on top of that. And that's why now in the Earth, we have a liquid core, and then we have mantle on top of that, and then on top of the mantle, we have the crust, which basically we live in this crust. Then the second stage was the bombardment of the surface of the Earth. And many scientists believe that shower of meteorites were hitting the Earth and carried water molecules along with them, and that's why we ended up getting the water on the surface of the Earth. And then we have what's known as flooding by molten rocks. So you can see in the in this second photo here, where you can see the effects of the bombardment. And when you look at the moon, you may see these very clear. But then we have another stage where we basically have flooding, and that it changed the surface a little bit. And then we have what we call surface erosion. And now the Earth, basically, you do not see any of these features of the bombardment anymore because of what happens of the geological activities that basically took shape on the surface of the Earth. Now, just in case if you're trying to understand why the Earth is so hot inside, it's basically because of potential energy, which is what falling material, and radioactive decay. Some of these materials are radioactive and they're releasing energy, and that was basically the source of the heat. So when we look at how the Earth has a change since its formed, okay, we know that the Earth formed rapidly from a solar nebula, and it was hot enough to be molten, and that basically about 4.6 billion years ago. The Earth has passed through 4 stages as it has evolved: differentiation, then cratering, and then flood by lava and water, and slow surface erosion. That's basically the stages that the Earth went on. We think of the Earth as is peculiar, and the reason for this, it has large amounts of liquid water on its surface, and that basically was the driving force for the surface erosion and the geological activities that we see on the surface of the Earth. And many believe that the water basically came with meteorites coming from early bombardment, and were releasing these water molecule, and that's what basically led even to the cooling of the crust of the Earth, and finally water start filling in some of the basins. And again, the Earth is peculiar because it's the only known planet for us that has life on it, and the search, of course, for other planets that can be suitable for life is on, or even if there is intelligent life is out there. Now, when we look at the Earth that we live in, and we call it here the solid Earth, so how do we know of the interior structure of the Earth? And I told you in previous lectures, you can go to hospitals and you use ultrasound, and the ultrasound basically can tell you about your internal parts without damaging them, and it has to do with the echo. And it can even image a fetus in the womb of his mother without basically damaging the fetus. So here, to study the interior of the Earth, we need something that we call seismology, which is seismic waves. So we need basically to send them waves that can shock, okay, the Earth, and then we can study about the interior of the Earth. Now, we have two types of seismic waves. One waves that we call pressure waves, and another type what we call shear waves. Now, as you can see in the cartoon here, you hit a grid like this with a hammer, so you are basically causing a stress on it. And as you can see, this basically go through the grid, but it only compresses and decompresses and so on. It's like a vibration back and forth. And this is what a pressure wave is. Shear is different. Basically, shear, you actually shear the material. You change the way its shape. And this is what we think of how shear basically exists. So as you can see on the top here, where we say we have the earthquake occurred in Mexico, for example, and then we look for these type of waves. First, the pressure waves arise, and then first S waves arrive later. And this basically can tell us something about the interior of the Earth. So now I will just try to make a small analogy here. You know that if you take a pencil and you put it in a glass of water, the pencil looks broken. You take it you take it outside, it's not broken. And the reason for that, it's because light refracts when it goes into a denser optical medium. So waves do that. Usually waves basically refract and bend when they go through different media with different densities. So when we look at the Earth and we have, let's say, an earthquake that happens here, and it will send a seismic wave through the interior of the Earth. Now, we can see here at this location here, some of these waves basically go inside and diffract outside, and we see pressure waves and S waves. There is a region here, okay, where you can see no pressure or S waves. It's like getting nothing. And there is a region here we only see P waves, and we don't see shear waves. And these waves, as I told you, it's like any other waves. Waves basically, when they travel through different media, they do refract. So pressure waves can go through something which is could be solid or semi-solid. But when it comes to and shear waves as well, it can shear it and change its shape. But when you go through something which is like liquid, well, in that case, pressure shear waves cannot shear liquid. Okay, so they cannot change their shapes. And what you end up getting, basically, you're getting a pressure waves. So scientists basically start learning as they go around the Earth. Why do in some region we have S and PNS waves, why in some regions basically we do not detect any of them, and why in some region we only detect pressure waves and we do not detect seismic waves. And with this, basically, they start making the analysis and learning about the interior of the Earth, which came clear that the Earth basically has a crust that we run, and below the crust you have a mantle, which is basically molten rocks or light rocks, and then below that you have a liquid core mainly made of iron, and then at the center of that you have another core which is kind of solid, which is made of liquid and nickel. And this is, of course, this is the main structure here, the mantle. Then you have this is the crust that we have here, and then you have the mantle, which colored here as orange, and then you have the liquid iron, what we call our core, and then we have the solid iron core here. So that's basically the Earth interior structure. You have a crust, and around below the crust we have the solid mantle, and then we have a liquid core, and inside this liquid core we have solid inner core. And some may say, they question how come we end up getting a solid inside something which is liquid, and the temperature of the Earth is so hot, we should not have something that is solid there. Now you can look at this curve that we have here, and we have two curves, the red curve, which we call the melting point, and we have the blue curve, which we basically say it is the actual temperature. So as you go toward the center of the Earth, you can measure the temperature, and of course you have some material there, and each material basically has a known melting temperature. So as you go from the in the mantle and you look at the melting point of the mantle, it is higher than the actual temperature. So the material is not going to melt, it's soft, okay, because the temperature is very hot. So as you go from, let's say, the surface all the way down to a little bit less than 3,000 kilometers, you basically have this mantle, and we define the melting point as the point where the material basically starts melting when it goes to when it goes into liquid. Now, as you go and you hit this point here, the melting temperature and the actual temperature of the Earth are more or less the same, and you can see here in this part here, the blue curve, which is the actual temperature, is higher than the melting temperature, and that's why we have a liquid core here, which is made of iron. Then when you get to a little bit more above 5,000 toward the center of the Earth, the melting temperature becomes a little bit higher, and the reason for that, temperatures are also affected by pressure. So any material that you have, pressure and temperature have the effect. So when the pressure becomes very high, the melting also temperature becomes higher. So in this region here, where we have this, the melting temperature is higher than the actual temperature, and that's why we have a solid core in the and we call this the inner core, and becomes what it becomes solid. So that's basically why do we have the structure that we have here for the Earth. Of course, you know that we did that in previous lectures when we talked about the diameter of the Earth, and we said the diameter of the Earth is equal to 12,756 kilometers. So if you want the radius, you basically have to divide d by 2. Okay, and that's why here you go all the way to 6,000 something. Okay, that's toward the center, from the surface all the way down to the center. Now, this liquid core that we have, it's basically made of iron and nickel, and these are highly conductive because they're hot, so they become ionized. And then we have convective motion. We talked about convection when we did that in chapter number 8 when we discussed the sun. And we said basically heat will, or hot material will rise and cooler material will come down. And that basically caused convection. And this convection basically caused the motion of these conductive ions. And when you have charges that can move, they will produce electrical currents. And electrical currents can produce magnetic field. So if you look at any cable that you're connecting to a plug in the wall, and you bring a magnetic compass and you go around the wire, you will find that the magnetic compass is affected by the cable, and the only thing that the cable has basically is a electrical current which produces magnetic field. So this liquid core in the earth, which due to convective motion of these ionized iron and nickel particles, they can basically generate magnetic field, would generate them in the form of a dipole magnetic field, which is basically north and south. And you're all played with, you take a magnet bar, you take a piece of paper on top of it, and you bring iron filings and you sprinkle them on top of the paper, and it gives you the shape of the magnetic field that we basically see here. So that's this liquid core. It produces a magnetic field, and that's basically the north and the south of the magnetic field. And you have to be careful now. The Earth is rotating around an axis that extends from the North Pole to the South Pole. We call this geographical north. Now, the magnetic north is different. The axis of the magnetic field, actually, there is about 11.3 degrees between the axis of rotation, which is go from the North Pole to the South Pole, and the magnetic axis. Now, you know that in chapter number 2, when we talked about the Earth, we said that the axis of rotation of the Earth is tilted at an angle of 23.5 degrees relative to the plane of the orbit of the Earth around the Sun. And we said this is what was responsible for seasons. Now, the magnetic field here is not really on the same axis. It is making an angle of about 11.3 degrees. So you have to be careful when you're looking and taking direction, and always people always saying this, is it geographical north or magnetic north? Because there is a difference. And you also have to be careful because when you're using a magnetic compass, the magnetic compass is also affected by any sources of magnetic field. And the magnetic field of the Earth is not that strong. So if there are any other sources around you that can produce magnetic field, they may give you an erroneous direction for your needle. Okay, so you have to be careful with that. Now, this magnetic field, it is basically a protection for the Earth. In chapter number 8, when we talked about the sun and we talked about the solar winds, and we said these winds basically come at a very high speed. They range from 300 to 800 kilometers per second, and they're highly ionized. And if they actually interact with the atmosphere of the Earth, they will burn it. But lucky enough, we have this magnetic field that we have around the Earth, And this magnetic field does not stop the solar wind. It only deflects them away. So you can see here, as the solar winds are coming, they're being deflected away. We have something that's known as the Van Allen belts. And this is basically where we trap some of the ionized particles. But due to the shape of the magnetic field, some of these ionized particles, they basically can leak in close to the North Pole and close to the South Pole. And when they actually leak, that's not all of it, it's only a small amount, and this small amount will basically interact with the atmosphere of the Earth. They are very highly charged energy particles, and they give rise to something that we call the aurora borealis. And sometimes they call polar lights. That means you can see them in the North Pole or in the South Pole. They are now known, or people refer to them as the northern lights, because most human activities happens in the northern hemisphere, and many have basically made expeditions to the North Pole, and they've seen these aurora there. So they are seen, and that's why they call them the northern lights. Now we know these also happen in the near the South Pole as well, and they may be referred to as polar light. And this is basically come as a result of the small amount of solar winds that basically get into the North and the South Pole due to the shape of the magnetic field of the Earth. And of course, we have what we call the Van Allen belts, where this material is trapped. So that's basically what you have. You have basically the sun, which sends in these solar winds. They come in and they basically find the magnetic field. And if you remember what I told you about the actual axis, where you have a North Pole and South Pole, and this is the magnetic axis here. So there is a difference of about 11 degrees, but whatever basically deflected away or being trapped in the Van Allen thread, the small amount that basically leaks into the North and the South gives rise to these interesting phenomena that we see in the North and in the South Pole. Is this clear? Any questions so far on this? Any questions? So the Earth basically has a protection shield which coming from the magnetic field, and it has to do with this liquid iron that we have there. So that's something that we have to keep in mind. When we look at the surface of the Earth, well, 2/3 of the surface of the Earth is covered with water, which is very essential to life. And of course, we have an atmosphere that keeps everything in. So even the water that evaporates will go up and eventually come down as rain. It's a closed system. And I always joke, maybe the water molecules that you're drinking now, maybe someone else before you have drunk them. Okay, so it could be looked at this way. And we have mountains, and we'll talk about what gave rise to these mountains. But of course, the water also plays a role in eroding its way through these mountains and giving them these jagged surfaces. Now, the Earth itself, the crust that we have on the Earth, I always look at the Earth as like an egg. And the egg, you have a crust, and then below the crust you have the white, and then inside it you have the white yolk. So here in the Earth, you basically have a crust, And below the crust, you have the mantle. And of course, below the mantle, you have the liquid iron. And inside the liquid iron, you have also a solid core, which is made of iron and nickel. But our crust here, it's not something which is solid all the way. It has breaks in it. It's like plates. And these plates basically over the top of molten rocks, which basically like a jello, and they can move and so on. And these, what we call tectonic plates. So, and these tectonic plates basically move and could change the surface of the Earth. So, if you look here, and this is, if we go inside the oceans, we may see some of these effects. When you see one tectonic plate basically is moving toward another one. So one is basically what we call a subduction zone, or maybe they're going away from each other, and we call this mid-ocean rise, for example. And when this happens, they may actually, you have an earthquake or you have volcanoes, and these can result sometimes in tsunamis and things like that. And we'll give you the volcanic activities, or they may give you earthquakes that we see. So there is a map here which shows you the active volcanic region, or map of the tectonic plates. And this basically tells you if you are close to a fault line, you're away from a fault line. So there are countries, for example, like Iran and Turkey, from time to time, you always hear, especially this year, you always hear that earthquakes have taken place because they're very close to a fault line. Japan, for example, they also are prone to earthquakes. Hawaii, which is in the middle between the United States and Japan. Okay, they have volcanic activities, and you can see lava usually comes down, and it has devastating effects sometimes on the forest or the people who live there, burning their houses and so on, and livelihood. So when we look at this, the surface of the Earth, and if you go back to any of these, you can piece it together. You can see that these pieces basically can fit together. So what caused them to break away and move away from each other? And we say that this is basically happening because of the tectonic plate movement. So scientists basically can look at the history of this tectonic movement, and 200 million years ago, the solid surface that we can see from the Earth was one piece, and we call that Pangaea. And 135 million years ago, it break up into a northern and southern continents. And about 65 billion years ago, you can see now the movement of these different continents when they move away from each other. It's like Africa and South America was one piece before. You can see the Indian subcontinent was far away from here. And then finally today, that's what you have. And this Indian subcontinent, when basically pushed against Asia, that's where basically you start getting the Himalayas, mountains, and so on, because you have mantle, and the mantle is soft material, and when they end, it starts moving up and up, and you basically start forming mountains. And we can, geologists, for example, they can take different rocks and they can do radioactive dating and so on, and they get at the ages. So 200 million years ago, we think that we have only Pangaea, and now it breaks apart because of this tectonic plates. If we want to look at some history of geological activities, where we can take fossils and we start studying them. We know that 4.6 billion years ago, that's the start of the formation of the Earth. Around midway between 4.6 and 4 billion years, we had the heavy bombardment that the Earth basically was subjected to, and it was very hot place. And here, around 3.5 billion years ago, some indication of the oldest fossil life was found. Now you come here, and you know, when we talked about the breakaway of Pangea, and we have the age of the dinosaurs, and now we basically have the formation of the Grand Canyons and so on that may come as a result of water erosion and things like that. So that's on geological scale. And we live in the surface of the Earth here, and we can basically look at all of these things. It would be interesting if these can be done on a different planet. So to conclude or to summarize this part, what is the inside of the Earth like? Seismic waves generated by earthquakes can be detected by seismographs all over the world and can reveal the Earth's internal structure. We basically talked about pressure waves, which we call P waves, and we talked about shear waves, which is S waves. Observations show that S waves cannot pass through the Earth's core because it's made of liquid, and that's basically where it's a strong evidence of the liquid core of the Earth. The Earth's magnetic field is generated by the dynamo effect, which is in our case it's due to the convection of these highly conductive ions that are moving, causing electrical current, and electrical current, of course, basically electrical current and the convection and the rotation of the Earth as well, giving these currents, and these give rise to the magnetic field. Of course, the magnetic field works like a shield for us, and it shields us from the solar winds, and it produces something that we call magnetosphere. And we have something that's known as the Van Allen belts, but whatever basically is leaks in from the north and in the south can give us the effects of how these can basically damage or interact with the atmosphere. And the Earth is dominated by plate tectonics, and that's why it's broken into the shape that we see now. Tectonic plates are made of low density brittle rock that floats on hotter plastic layers of mantle. Mantle is jello like, and volcanism and earthquakes are common along the edges of the plates, and sometimes we refer to these as fault lines, and if you are close to these, then you're prone to volcanoes and earthquakes. We talked about the continental drift and how these are basically drifting, and we just gave a brief geological history of how we view the Earth. The atmosphere of the Earth, and that's also a good question that people always ask, how did we end up getting the atmosphere of the Earth? We know that the atmosphere of Earth is composed of gases, and these gases are basically nitrogen, and it's given by weight, by mass. And remember, I told you about before when we talk about atomic or we talk about mass percentages. So 75.5% is nitrogen. Oxygen is 23.1%, which is very essential for us. Then you have other elements like argon. And then you have here CO2. And CO2 that now you basically trying to say we have to use a cleaner energy in order to avoid the release of carbon dioxide in the atmosphere, which could cause problems. Well, carbon dioxide is important because trees, they do something that's called photosynthesis, and they take sunlight and carbon dioxide and they produce oxygen in the way. But if you have higher concentration of carbon dioxide, and this is also, some people say, when you cut trees, less CO2 is consumed, and that's why when you end up getting what we call global warming. So how did we get this atmosphere that we have in the Earth? Well, we have the outgassing, because you have hot material, and this material basically is releasing gases, and in the volcanic activities as well. And then we have the later bombardment with icy meteorites and comets that start releasing basically water and water vapor and maybe gases and so on. And that's how we got the atmosphere of the Earth. This here, it shows you an image of an active volcano, and you can see hot material basically is gushing out from the Earth, and it's very hot. So when it comes to the atmosphere of the Earth, well, you look at the clouds here, and then you look at Mount Everest, so they're very close to do it, and the clouds usually made of water, vapor, and so on. And then we have on the top the ozone layer, and the ozone layer is basically very important to us because it's made of oxygen-3. You're all familiar that when you talk about oxygen, it's always O2, but the ozone layer here is made of it's made of O3, which is 3 oxygen, and this is basically makes it, it blocks in the UV that comes from the radiation of the sun, and these can sometimes cause cancer, skin problems, and so that's our protection there. So we need that atmosphere, and of course, gravity worked in keeping the atmosphere where it is, not for these gases to escape from the Earth. And there are many factors that basically depend on the abundance of the water vapor that we have in the atmosphere. And you know, rain comes as a result of water vapor that goes up, it condenses, it gets a little heavier, and then basically it rains down. Now we come to the greenhouse effect. And the greenhouse effect, basically, it's something that people use in houses where they take a glass and they try to trap in the sun heat to raise up the temperature and so on. It usually comes from infrared radiation. The atmosphere of the Earth basically is doing that. It's doing the greenhouse effect for us. And that's very important. That's what gives us the comfortable temperature that we have here on the surface of the Earth. So we need that. So the greenhouse effect is important for us. CO2 is important for us. We need that. But problems start arising when we can see here that the level of CO start increasing about the Industrial Revolution. The discovery of coal and then petroleum and burning them as a source of energy, they start basically releasing CO2 in the atmosphere, and that increased the concentration of that. And of course, that will trap more heat. And if it traps more heat, it will lead to something that we call global warming. And of course, that will reduce the solid land that we can basically live on, and the water will basically start reducing this. And people always look at the North Pole or the North Cap and the South Cap, and they look at they are melting because of this increase in temperature. So there is a graph here at the bottom here where we show you the effects of the increase, and it comes with the Industrial Revolution. And now we have lots of cars that basically are emitting CO2, and we want to shift to something that's more friendly to the environment. So the heavy human activity and the emission of CO2 and the deforestation. Many people are basically cutting trees for furniture, and sometimes they used to make paper from it, but now probably we can go electronic, so we don't need to do that as much. That will cause basically the greenhouse effect, and this is what we call global warming here. So we have to reduce our dependence or our use of energy that produces CO2 in the atmosphere. And if we have high levels, that of course will melt the polar caps either north and south, and that will give rise to higher level waters where the ocean will rise, and we lose a dry land. These are basically the effects that can happen in our own atmosphere. Another effect that was noticed in the 80s, it was basically the depletion of the ozone layer. And it was found that fluorocarbons, it's a material that's used in cooling systems. It escapes and it will basically react with the ozone or O3 and breaks that. And of course, that basically will reduce the ozone layer. And if this goes, then we basically have a problem with the UV that will come in. And now there are good news that there are restrictions and using the CFCs, and we have to have better control and getting them released in the atmosphere, which basically can reverse the effect of on the ozone. And there are good news that the ozone, or what's known as the hole in the ozone layer, basically has been now decreasing due to this. So when you go to the atmosphere, you may have different layers, which you call the ionosphere, the mesosphere, the stratosphere, the clouds, the troposphere. Okay. So these are some old images taken of the ozone layer, and just to see that how it is basically closing up, and that's a good news. So we talked about the Earth in terms of the internal structure of the Earth, which is basically the crust, the mantle, the liquid core, then the solid core. And we use seismic waves basically to get at this internal structure of the Earth. And then we talked about the tectonic plates that we have on the surface of the Earth. These are summaries that you see in these slides are basically what we already mentioned. And then we came to talk about the atmosphere, and we said the atmosphere basically is formed from gases that's either coming as a result of degassing or the radioactive or the meteorites that were basically bombarding the Earth, which actually brought water with them. So the Earth here that we look at is a clear example of a planet. We live here, we basically know more about it, but there are concerns now. What happens if we have to leave? Where do we have to go? So we really have to look at a planet which is in the habitable zone, as we discussed in chapter number 6, and it can support life. Now, scientists believe that Mars lost its atmosphere due to solar winds, and that's why it doesn't have the comfortable temperatures. Just to add with some, we end up with some common misconception. People think greenhouse is bad. Actually, we need the greenhouse. The greenhouse is basically what gives us the temperature that we need. And we need CO2 because of the photosynthesis that we basically need for the trees to produce hydrogen. But it is the human activities of putting out more greenhouse effects out there that might give rise to the average temperature of the Earth, which will lead to something that we call global warming, and that, of course, will melt the caps either in the North Pole or the South Pole. So the Earth here is an example of a planet that we basically can study, and we can compare other planets to it. Any questions? Any questions on this? Any questions?